Now, I will not get involved on the cost, right? Okay. Except, I will tell you one thing. Economic justification for using capacitors, right? And so the first is release generation of capacity. Why? Because you reduce the current that the generator has to provide. Today we were talking about wind farms, right? What's happened with a wind farm? Well, the cheapest wind turbine is an induction generator. But to start the induction generator, you need to provide leading reactive power. Wind farms normally are not located across the parking lot. They are normally in areas that are very windy. Normally they are farmland away from the low centers. And so if you have to provide that reactive power which is leading to start the wind farm, what's happening? You are going to operate at a very high voltage, right? Because just put Q equal to a leading power factor, and there is an equation here, right? Sorry, a graph that shows that the voltage is going to increase. Oops, oh here, right? The voltage is going to increase, right? Well, you have to keep it within the maximum and minimum value, right? In this case, for example, without capacitors, you got it there, right? So here you need to put either voltage regulator or do something, right? And here, if you look at that, it says feeder with uniformly distributed load. It doesn't exist, right? It's very theoretical. The other is at heavy load. What do we call heavy load? Peak load. And the other is light load. What do we call it? Minimum load, right? So here you got the two figures. And so that's the problem with wind turbines. So what do? You put capacitors, right? Obviously, there are other types that are dealt differently. You know, you can go to a doubly fed induction generator, or you can go to a permanent magnet synchronous generators, right? And so you have different. Now, release transmission capacity. Why? Because you have less current. Right, the conductors have a certain thermal limit. Thermal limit. What is the thermal limit? The thermal limit is that current that causes a heating of the conductor and the conductor starts sagging. And then the distances to ground are not maintained anymore. The minimum distance that are specified by the National Electric Safety Code. So there is a thermal limit, and so if you reduce the current, you can transmit more power. Release distribution system capacity, because now there is less current that coming from the substation, right? That's what we saw last time. And additional advantage R, reduce energy copper losses. Benefits, right? We have a reduce of the current, so now we got a 26% additional capacity at the substation, right? Here we look at the losses, right? So reduce energy copper losses, reduce voltage drop, and consequently improve voltage regulation, right? That's what we saw. Release capacity of feeder and associated apparatus, right? What is release capacitor? Release capacity, sorry. What is capacity? Rated power, right? Sometimes capacity could mean current, rated current. What is the capacity of that load, of that source? Well, it can give you 100 amps. Obviously, if you multiply by the voltage, what's happening? You get the rated power. So capacity is related, right, to sources most of the time, and is rated power. It's like demand. What is demand? Complex power. And it's associated with what? With loads, right? So the difference in terminology. Postponing or elimination of capital expenditure due to system improvements and expansion. Well, this is what they're talking about, the benefits of distributed generation. If I need 10 megavolt more into this area, because now we are going to have a Hilton on the corner, right? Then we are going to have a shopping center, whatever, the expanding. You need to bring that power. If you have distributed generation, if you have a fuel cell that is using gas, I don't need to bring the power inside the area because I can generate 10 megawatt using this fuel cell. That's distributed generation. So that means that I don't need to install another power transformer at the substation. I don't need to upgrade. Well, I don't know, you haven't been there for too long, but those big metallic towers that you have there, they were not metallic towers a while back. The voltage wasn't that voltage either. But because of all the loads increases, the Walton Arts Center, the University of Arkansas, you know, what are we doing with Ozark Hall? Are we going to improve it, adding more wings? So what is going to happen to the load? It's going up. You are adding more buildings on campus, so what's going to happen? That's the reason why the utility upgraded the sub-transmission system, because you have to get that power there. And the university doesn't have money to do distributed generation. You know, we like to thank the professors, but it costs money. So, that's what says postponing or elimination of capital expenditure. Now, it's very hard that you, by just doing power factor correction, you can fix everything. Revenue increases due to voltage improvements. I don't believe that. Well, I don't know what the author is thinking of that, right? So if your voltage goes from 95% to 100%, what's going to happen? Right, exactly. More power out of the load, right? Because the voltage is higher. When you calculate the current, what do you get? More current. But that's assuming that you have a constant resistance or a constant inductor, right? So if you increase the voltage, the current increases. If the current increases, what's happening? Your kilowatt hour increases, right? Well, how much are they going to increase, right? Are those going to make, you know, I don't want any of you going to the newspapers, you know, the utility is doing that because they want money, right? So really it's hard, even that you can put it there, that there's going to be perhaps more power, more current, so theoretically there will be more revenue. Don't think that if the company is going bankrupt, the utility company is going to be saved by that, right?